So this lesson really covers what we reviews what we covered last class and goes a little bit further in terms of describing the right fist rule and the right hand rule. Okay, these rules are going to be used, practiced in the various worksheets. Okay, so just as a review, what we're talking about here is electricity and magnetism, and what the magnetic field is going to look like. Magnetic field is similar to the electric field and the gravitational field, and this field will provide a force on a charge that is going to be moving in this field. Okay. So I'm going to go through the next several slides fairly quickly, but electricity and magnetism combined make up the strong force. The other three major forces is gravity, which is the weakest force, and then we have the strong nuclear, which is the strongest force that we know of, and the weak nuclear, which is between electricity and magnetism and the gravitational force. Okay, all of electricity and magnetism can pretty much be summarized in the four Maxwell's equations that we looked at last time. Okay, the four Maxwell's equations are beautiful, however, they do require an understanding of complex calculus. So first off, magnetism, magnets have a north pole and a south pole, and opposite poles attract each other and like poles repel each other. The opposite poles, the north pole could be it would be similar, very similar to the positive charge, and the south pole would be very similar to the negative charge in the sense that the magnetic field leaves the north pole and goes towards the south pole. Okay. Magnets come in magnetic dipoles, so we cannot have just a north or just a south. In fact, that's the primary difference between magnetic magnets and electric charges. Okay, electric charges we can have just a positive or a negative. Magnets we have to have a north and a south together. Okay, so when I look at the field, magnetic field generated from a bar magnet, I basically have the magnetic field leaving the north side of the magnet, going to the south side. This looks very similar to the picture we had for a two charges, opposite positive and negative. Okay, we described this kind of as like mitosis and cell division. Okay. Similarly to electric fields, we can have uniform magnetic fields where I have a north magnet facing a south magnet. Okay, the magnetic field is measured in Teslas. Okay, Earth's magnetic field at the surface is roughly 50 microteslas, just to give you a sense of how strong Earth's magnetic field is. We're going to be using three-dimensional vectors, so just to remind us, a dot in a circle represents a vector that is coming out of the page, and an X in a circle represents a vector that's going into the page. Okay, this kind of represents the head of the arrow and the tail of the arrow respectively. So when we look at the magnetic field from a wire, okay, the magnetic field from a wire is going to be circular around that wire because the wire carries moving charges, the current. Okay, so if we look at the conventional current, which is the flow of positive charges, in this picture, the current is flowing towards the top of this screen or top of the page, and the magnetic field is curling around behind the wire and then back in front of the wire. Okay, kind of as shown there. And that's going to be important because we're going to be using what we call the right fist rule to determine whether the magnetic field is going to go clockwise or counterclockwise. Okay. For the magnitude of the magnetic field, what's important to remember here is that the strength of the magnetic field is going to be proportional to the current, stronger magnetic field, and weaker with respect to R. Okay, so greater R, weaker magnetic field. Okay. So the right fist rule is this. Okay, in all of our right hand rules, the thumb is going to represent the direction that the positive charges are moving. Okay, so since current is the positive charge, what I would do is I would take my thumb, point it in the direction of the current. So if my pen represents the wire and the tip of the pen is the direction that it's heading, I take that and my fingers here will naturally curl around the wire no matter how I orient it. Okay, and so the magnetic field in this case, if the magnetic field is pointing to my right, okay, then if the current is pointing to my right, the fingers of the right hand naturally curl around this wire. So looking at it, okay, above the wire, my fingers point towards me, and as I curl them around, the fingers point away from me below the wire. And that's how the right fist rule works, okay? It tells us the direction of the magnetic field from a wire carrying a current. Okay, we're going to skip these because you have some worksheets that will do that. So I'm going to skip to the next slide. And the next slide is basically the Lorentz force. Okay, this is the force that a moving charge experiences when it moves in a magnetic field. Okay, the magnitude of this force, okay, is given by the formula on the bottom. Okay, the force is equal to the charge, okay, in coulombs, times the velocity multiplied by the magnetic field B. We use the letter B to represent the magnetic field. Okay, so although I say multiply, this is not your standard multiply because velocity and the magnetic field are both vectors. Okay, this is actually what's called a cross product. It's one way of multiplying two vectors together. The result is another vector, but really we're just not going to worry about the direction. Here, what we're going to worry about is the magnitude. Okay, so if I'm just concerned with the magnitude, then it's Q, the charge, V, the velocity, magnitude of velocity, B, the strength of the magnetic field, times the sine of theta, where theta is the angle between the velocity and the magnetic field. Okay, so the force is going to reach a maximum when velocity and the magnetic field happen to be perpendicular, or when theta equals 90 degrees. Okay, because sine of 90 is 1. It'll never be larger than 1. Okay, so then we basically have just Q, V, B. And most of our situations will have a 90-degree orientation between the velocity and the magnetic field. Okay, so that gives us the magnitude. The direction is going to be derived by the right-hand rule. You must use the right hand, or you'll end up with the wrong answers. Okay, so in terms of the right-hand rule, there are 4 letters in F equals QVB, and all 4 of those letters are going to be represented by your right hand. Okay, the thumb again is going to be velocity, or the direction that the charges happen to be moving in. Okay, so your thumb is velocity. The fingers, the remaining 4 fingers, are the direction of the magnetic field. Okay, so B is going to be represented by the fingers because there's multiple arrows representing the magnetic field and you have multiple fingers. Alternately, if you know American Sign Language, B is this symbol where you just have the 4 fingers straight up. Okay, and then F is going to be where your palm points. Okay, so keep your hand open, okay, the thumb open and flat, so don't orient the thumb towards you. Okay, keep it open and flat. Try to keep a 90-degree angle between the thumb and the rest of the fingers. Okay, and orient your thumb in the direction of velocity, your fingers in the direction of the magnetic field. Your palm represents the force. Okay, what's not represented, or what I haven't told you yet, is Q. Okay, Q is a scalar, so it doesn't have a direction associated with it. However, it can be positive or negative. Okay, so if Q, always double check it. Okay, if Q is negative, then the force is actually going to be the back of the hand. Okay, or what I actually suggest doing is whatever answer you get, okay, I'll give you 3, you have to find the 4th one. Okay, whatever answer you get, you have to just flip the direction, because that's all it means. Okay, it means your velocity. If you said my velocity is going to the left, then in reality, if it's a negative charge, my velocity is going to the right. Okay, so let's look at this picture. Okay, again, here's an example. Your thumb is velocity, the magnetic field is given by the fingers, your palm is the force. And then we double check to see, is it a positive charge or a negative charge? Orient your fingers or the palm according to whichever 2 vectors I give you. Okay, Sometimes I'll give you all three and you have to find out the sign of the charge, but mostly I'll give you two vectors, find the third. Okay. So I can expand this because most of the time I don't really have charges moving in space. Okay, so instead what I'm going to have is the force on a wire, okay, because my charges move on a wire. Okay, so in this case, the force on the wire is going to be equal to the magnitude of the magnetic field times the current times the length of the wire inside the field. Okay, so if there's a length of the wire outside the field, it doesn't count. Okay, this is the formula that I described as the F-Bill formula. Okay, so again, it kind of makes sense. Okay, a stronger magnetic field, stronger force. Stronger current, more charge, more force. More wire, more force. Okay, at the end of this formula, okay, is that sine theta that we have again. So if the wire is oriented not perpendicular, okay, if the wire is oriented at an angle to my magnetic field, that's the theta. Okay, and again, we use the right-hand rule in this situation. Okay, again, your thumb represents the direction that the positive charges are moving. In this case, current. Okay, your fingers are still the magnetic field. Your palm represents the force on the wire. Because the charges are stuck in the wire, if I move the charges, I move the wire as well. Okay, so again, thumb, direction that it's traveling, sort of like what you would imagine to do if you were hitchhiking. The magnetic field represented by the four fingers and the palm. Okay, again, if it so happens to be negative charges moving, remember to flip your answer. Okay? The rest of these are just problems which I'll leave for your worksheet. Thank you.